Okay, on to chapter 10. So like that. So these are we're going to be talking about alkyl halides, right? So I think this is one of those where we've been talking a little bit about chlorides or about halides before, but they wanted to sort of summarize a lot of the different things in this chapter. So like that. So the first thing obviously we always end up doing, right, is naming alkyl halides, right? Naming the new group, right? So these actually have the exact same naming rules as alkanes. Okay, so there's absolutely no priority given to the fluorine, chlorine, bromine, whatever, right? So it's not like the alkenes, right, where you the one at the end closest to the functional group gets the priority. This is no different than the halides do not get this priority. They're just like alkanes. Okay, so for that, so alkyl side chains, right? So, but if it's fluorine, all right. So we've seen this before, right? So fluorine it becomes fluoro. If you have a chlorine atom, it's chloro, bromo, and iodo. Okay, so like that. So, but again, it's naming, right? So here we go. So right, bromine, right? So put in the dots for your carbon chains, right? For your carbons. Okay, so here we go. So we need to find the longest chain, right? Don't forget to go down the side chains, right? So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, right? 1, 2, 3, 4. Well, it's looking like it's gonna be 6, right? And just historically, I prefer the horizontal chain, but it wouldn't really matter. Okay, so here we go. So it's 1, 2, 3, 4, 5, 6, right? So it's C6, right? So that's going to be hexane. Okay, and so the side chains are going to be this bromo, right? It's bromine, so it becomes bromo. That methyl, right? This 2 carbon piece, which is ethyl. Okay, so if we're going to do right, so we need to check both sides, right? So if it's 1. We're going to go from the left side, it's 1, 2, 3, 4, 5, 6, right? So that means the bromo's off of 2, the methyl's off of 3, and the ethyl's off of 4, right? But then we also have to check from this side too. So 1, 2, 3, 4, 5, 6, right? So we're naming just like the alkanes. We have to go from both sides to check, right? So in this case, the bromo will be off of 5, this will be off of 4, and that'll be up to 3, right? So we add them up. Right, so that's 5. That's 9. It's 9. This is 12. This gives the smaller number, right? So we're going to use this numbering group. Okay, so then the question becomes which comes first, bromo, methyl, or ethyl, right? So it's bromo comes first, so it's just going to be 2 bromo, right? So then we say which comes next. Is it methyl or ethyl? In this case, it's ethyl, so it's 4 ethyl, right? And then 3 methyl hexane, right? So we have a main chain that's 6, right? We have a methyl group hanging off of it. Where's it hanging off of? Carbon 3. Right? We have an ethyl group, right? Ethyl, hanging off of carbon 4. Right? Carbon 4. And then we have a bromo that's hanging off of carbon 2. Okay? Not too bad. Okay, so that, right? So we'll put in our carbons, right? So 1, 2, 3, 4, 5, 6, 7, right? So with that, so 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, right? So it's gonna be C7, C7, right? So it's gonna be this guy here, right? Okay, so it becomes heptane. Right, so then the functional groups, right? So they're that chloro, all right, and then this methyl. Okay, and so right, so if we started right, so we need to do left and right, right? So if we do 1, 2, 3, 4, 5, 6, 7, right? So the chloro is 3, right? The methyl is 5, right? And then if we do 1, 2, 3, 4, 5, 6, 7, right? So here the chloro is at 5 and this one's at 3. We add them up, they're both 8. Okay, and so we have an absolute tie and there's no way that we can break it, right? So in that case, right, the first the first alphabetically gets the lowest number. Okay, so we're going to end up choosing that guy there, right? The first alphabetically gets the lowest number. Okay, so it ends up being 3-chloro, 5-methyl heptane. Okay, not too bad. All right, so last but not least, we've got this. Chloro, CH3, right? Okay, so, right, so our main chain is going to be this, right? It's not going to be this one carbon chain here. It's going to be the ring, right? So it's C5, right? So normally that would be pentane, right? But to indicate that it's a ring, right, it would be cyclopentane. Okay, so then we've got the these three functional groups, right? So chloro, methyl. Okay, so here we go. So we're going to say each one of these carbons is number 1. Let's see what happens with the number, right? So if we do 1, 2, 3, 4, 5, right? So this chloro would be 1, this chloro would be 2, that methyl would be 3, right? So like that. So if instead we did, right, 1, we go towards the nearest neighbor, right, but it doesn't really matter in this case, so we'll do 1, 2, 3, 4, 5, right, because they're equidistant, right, so it'll be 1, 5, 2, right, so, and then lastly, we're going to say this is number 1, and then we go towards the nearest neighbor, so in this case it'll be 2, 3, 4, 5, right, so it becomes 1, 2, 3, right? So we add these up, right? So it's 6, 7, 6, right? So it can't be this one, okay? But there's an absolute tie that we can't break, and so again, we go to the alphabetically, right? So chloro versus the methyl, right? So chloro, right, is the first alphabetically, so it's going to get the lowest number, right? So we're going to choose this one. So in this case, so in these 3 cases, right, the chloro ended up being nearest to that, but it just so happened to be in these 3, right? So if the chlorine was hanging off of here, or hanging off of there, or whatever, it wouldn't make a difference. Okay, so if we switched the ethyl and the bromine here, it would be 4 bromo, 2 ethyl. It'd still be here. It's not the bromine. It just so happened in this case, in these 3 cases. Okay, so here we go. So we use this numbering, right? So it becomes chloro becomes 4 methyl, so it becomes 1, 2 dichloro, 3 methyl, cyclopentane. Okay, not so bad. Okay, so radical halogenation. Okay, so this is one of the things. This is one of the crazier sort of reactions because it's exceedingly messy. It works, but it's messy. Okay, and so what can happen is you can hit chlorine with light, and it'll actually break the chlorine-chlorine bond, and it breaks it so that 1 electron goes on each side. So you end up with a chlorine radical, 2 chlorine radicals actually. Okay, and so this one you can react with an alkane CH, right? So it cannot be part of a double bond. It has a double bond attached, so it doesn't do this. So like that. But if it's an alkane CH, what ultimately can happen is that you can swap an alkane CH with a Cl. Okay, that hydrogen with a chlorine. Okay, it also works with bromine and iodine too, but usually just bromine chlorine. Okay, and so so if we have this. Right, so CH3, CH2. I'm just going to go ahead and draw this out. CH2, 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 CH3. Okay, we had bromine, right, and light. Right, so that's the H. That there it looks like HV, but it's not. But that's light. Okay, and so the question is, right, so is this going to be, right, is this a CH, an alkane CH? Yes, right, so we can get a reaction there. When that happens, right, so we swap out one of the hydrogens, or one of the hydrogens for bromine, right, so CH2, CH2. Right? Okay, what about this one? Right? So what about this one? Right? So well, that's a carbon, right? It's just single bonds, right? So we can put it here, right? So instead we can put that bromine there. Okay, and same goes with this one, right? Okay, and then that one. Oops, CH3, CH2, CH2, CH, bromine. Right? And then this one here, that also works. So it'll make all of these compounds, right? So all of these, right, you see bromine, 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 okay? But the problem is, right, if you notice, these two compounds are exactly the same. All you got to do is just take this bromine and flip it, and it becomes that one. Same thing with this one, these two. Okay, these two compounds, B and D, are exactly the same. If you take this and flip it, it turns into that one. Okay, this one doesn't have it corresponding. So really, there's only three compounds, three distinct compounds that it makes. Just those three. Okay, or alternatively, you could say these three. Okay, it doesn't really matter. Okay, but really, right? So with that, so it'll replace this. It just so happens that these two and these two are the same compound. Okay, so it gets quite messy. Okay. Okay, so same thing happens with these guys here, right? Now, why won't it react here, right? Why not there? It's because, right, it says 1, 2, 3, 4. There are no hydrogens, right? So with that, there's just carbons on here, so it can't react there, but it can react all these other places, right? So it can react, right, Cl. Right? Okay, so all of the here, 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 and here, those are all alkyl, right? Because there's no double bonds. Carbons with hydrogens attached to it. Now, the thing is, I won't go, right? So these three compounds here are actually the exact same compound. Okay, and so if you don't believe me, go and name the compounds. Okay, so like that. So the right, so they would all be named 1-chloro, 2,2-dimethyl, 2,3,4-butane. That's what all of these could be named just like that. So really, there's only three compounds, right? And so you just pick one of these and these two. Okay, so like that. So there's really only three. But again, you notice you get for doing a very simple reaction, right? You get a whole bunch of big mixture. Okay. Okay, so the last ones, we're going to take toluene here. Right, so remember there are hydrogens here, right? We add chlorine to it, light. Okay, but notice how all of these carbons here are attached to carbons with double bonds, right? So, right, there's no hydrogen here, so you can't even deal with that, right? But this one, right, it's attached to that double bond, right? So is that one. You know, all of these have double bonds, except for this one, right? So this is the only one that only has a single bond attached and has carbons on it, right? So really, the only product you can make is this. So, okay, you're not going to be able to react in any of these, right? Because they're attached to double bonds, right? But that's your product. Okay. Okay, now we've talked about adding bromines on there, right? So if you have a double bond here, right? So if you had just Br2, right, you're going to add directly across there, right? If you have HBr, right, you're going to add. In this case, you're going to get a mixture, right? Because they're both secondary, right? So with that, but there's another way you can put a bromine on there, and that's actually what's called. You can add to what's called the allylic, allylic carbon. Okay, and so all allylic means is it's one carbon away from a double bond. Okay, so in this case, this carbon here is the allylic, right? So here it's CH3. Actually, I should say it like this because it's trans. Right? Okay, so you're one away. So this is allylic. Okay, so here's the double bond, right? So you're one carbon away, so it's there, but then there's also the one here, right? So this is also allylic. Okay, this compound called NBS, N-bromosuccinimide, okay, NBS, will add a bromine to these allylic positions, right? So half the time it's going to go half the time it's going to add here, the other half is going to put there, right? Approximately. Right? The other half of the time, it's going to put it there, right? Half the time here, the other half there, right? So you're going to get, you're going to get a mixture of the two. Okay, so the way this works is actually NBS is actually can actually make a radical and it extracts this out, and so but this one here ends up being. We'll talk about this in a minute, but it ends up putting it on here. Doing a radical type mechanism, and essentially what you do is you swap the bromine on the NBS for a hydrogen. Okay, something like that. So okay, so remember, so if you have something like cyclopentane here, right? So yeah, just regular bromine, you're going to have it both sides, right? HBr, you're going to have bromine on one side. NBS, it's going to add to that allylic position here, right? It is going to go over on this side too, but that's the same compound. Same deal with this. So it's symmetrical. You only make one compound. Okay, so the reason why this happens is you can get resonance stabilization, right? So if you have like this, right? So if you have radical here. Right, what it can do is it can take, right, so remember these pi electrons here, right, it can take this one and combine them together, right, to make, and then this one has to go somewhere, so it ends up there, right, and notice I'm doing single fish hooks, right, oop, that's just a single bond. Okay, so you end up making a double bond there, right, and then right, so one of these was there and there, right, and the other one goes there, right, so you can get this resonance stabilization between the two, which makes it much more likely to occur. Okay, so the problem is, right, so you can get these things rearranging themselves, right, so if you have the allylic carbon here, you can get this resonance stabilization, right? So it actually ends up being, so when you run this reaction, the octene, what ends up happening is you get a little bit of where you would think it would go right there, but then also the double bond sort of rearranges itself onto here, right? So like that. So you can get these crazy rearrangements, right? So you can actually, depending on if you wanted to predict the product, right? So you have the allylic carbon here. Notice it's not symmetrical because of these two methyl groups, right? So you can actually get 4 compounds out, right? So if you add here, you can bring them down there, and so you can get the regular allylic product, but then you also have the rearrangement product here, or if you add to the allylic up there, you can get the regular allylic product, or you can get the rearrangement with the bromine there. It's just, it's a mess, stuff like that. So, okay. So, okay. So how do we make these alkyl halides? Well, the easiest way to do it, okay, or one of the ways that you can do it, is just throw in, is to start with the alcohol, okay? So with that, and so essentially what happens is the you can get this going, right? So you have something like this, right? Right. So if you have something like HCl, right? So these electrons, right? So remember these guys, electropositive, electronegative, right? So this guy's going to attack, go there. Positive charge there, plus chlorine minus, right? So this guy here is, right, it's always really good to leave water, or to have water leave, and so when that happens, you form a carbocation here, plus water. And since you have this carbocation here, this guy can come in and attack to make your chlorine. Okay? So the water leaves to leave a carbocation, to which the chlorine can come in and attack to substitute. The problem is, this is pretty slow because you have a secondary carbocation. Okay, so it actually works pretty well with a tertiary carbocation, right? So that actually happens fast. This is pretty slow. This is probably never going to happen because you'd making a primary carbocation, which isn't good. Stuff like that. So it really only happens with tertiary, sometimes with secondary, stuff like that. So how do you do it? If you need to make a primary, secondary, you actually switch the chemistry. And so these are 3 steps. We'll talk about this more, about the mechanisms of these later on, but these are just sort of reactions you need to know, stuff like that. So if you need to, so SOCl2, this is called thionyl chloride. This swaps OHs for chlorines. Okay, PBr3 swaps OHs for bromines, and HF pyridine swaps OHs for fluorines, stuff like that. So those are reactions just to know. Right, so this only works really with tertiary carbons, a little bit with secondary. But if you really want to make primary, it doesn't work at all with primary OHs. If you want to do that, then you have to switch the chemistry around a little bit. The other thing you can do with these, once you've made the chloride, okay, is do some very interesting chemistry. And one of the more important reactions you're going to learn in this course is the Grignard reaction. Okay, and so the reason why this is we're doing this is to make a carbanion, right? So carbon with a negative charge on it. Okay, and so so what you can do is you can attack electrophiles, right, and build carbon-carbon bonds, right? So what happens is you have a carbon with some sort of halide on it, right? So chloride. Okay, and so if you look at the electron, right? So in this case, right, the chlorine is going to be a little more electronegative, right? So electronegative, electropositive. And what you do with to make a Grignard reaction, you literally just mix it with magnesium, just magnesium metal, right? So like that. So magnesium turnings, whatever. And what that does is it inserts itself between the carbon and the halide. Okay, and so what that ends up happening is that this ends up getting a partial positive, which puts up negative, and a partial negative, right? So the difference between these two is now different, and so now you've made a carbon with a negative charge onto it. Okay, and so you've swapped the carbon with the positive charge with a carbon partial positive with a carbon with a partial negative. Okay, and so this becomes nucleophilic. And so if you were to say, if you had say, this compound, bromide, right? You mix it with magnesium, right? So now you've got the MgBr. And so essentially you've put this as a negative character there. And so if you mix this with, say, the chlorotoluene that you made previous to that, right? So now you've got, right? So now you've got partial negative, partial positive. Here you've got partial negative, partial positive, right? These are going to be attractive, right? And so this is going to attack there and kick off the chlorine to make right. And so you can see that here, right? And this part here is that part there, and then you've made this new carbon-carbon bond. Okay, so you can make it. You can make a stabilized carbanion. Okay, and this is this MgBr, with the magnesium inserted within. This is called a Grignard reagent. Okay, so like that. So the other thing that you can do is you can do this with just putting in lithium. It's the same. It's analogous to the Grignard. Okay, so if you had Br and you just threw in lithium, okay, just regular lithium metal. Again, it inserts itself. In this case, it actually replaces the bromine. But again, right, this is a more carbon's a more electronegative than lithium, right? So you go from a carbon with positive character to one that has negative character. But otherwise, it reacts the exact same way to a Grignard reagent. Okay, so with that, the problem is Grignard reagents are much more stable than lithium, than the carbon-lithium compounds, organolithiums. Okay, so with that, the other way you can do is what's called Gilman reagents. Okay, and so these, what they do is they actually insert copper. Okay, instead of so you actually make them from here, and so what happens is you actually you need two of these actually. You add copper iodide, okay, and so you end up getting copper replaced here, and then you actually get a second one added like that. Okay, and so this is again, this reacts just like a carbanion, right? Like that. So this is going to react just like a Grignard reagent. Okay, so like that. It just so happens you have two of them on here. So there's three different ways of doing the exact same thing. You'd either put a magnesium on there, you could put a lithium on there, you put a copper there. Okay, and there's reasons why you would want to do one, but for this class, just know it's just three ways to attack the problem the exact same way. Okay. Okay, so here we go. So if we wanted to, fill in what's missing, right? So with that, so bromine, right? So when we add lithium to it, right? So what are we gonna do, right? We're gonna replace the bromine with the lithium, right? So, okay. Whenever we add the copper iodide, right? We actually get two of these, right? So 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5, right? So down to the copper. Right, we also get another 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5, right? So you actually get two of them, right? And then if we add chlorine like that, right? So remember, this is electronegative, electropositive, right? Electropositive, electronegative, right? Just from this is going to come down and attack here, right? Kick this off. So you're going to end up with okay. So 1, 2, 3, 4, 5. So that's where these 5 come from. This one here comes from the toluene, and then you have the methyl group, right? So 1, 2, 3, 4, 5, and I'm missing a carbon here. So there should be an extra. Oh wait, I'm sorry. There actually isn't one here. It's actually this. I'm sorry. So I am okay. So that actually is there. But again, it's carbon positive, carbon negative, right? So this attacks there, and so we're good to make the carbon-carbon bond. Okay, another way you can do it is what's called, it's technically Suzuki Miura, your reaction, but everybody knows that it's Suzuki coupling. Okay, and so what this does is these are very distinct, right? Because you have this crazy boronic acid functional group, which is about the only time you ever see this. Okay, and so you have, say, something like this. Okay, and then you have a halide, right? Wherever this is attached, and the halide is attached, right? So there's actually a double bond there. Those two come together, okay, and then everything else just falls away, right? So you end up with, it's a very clean reaction, right? So you need a palladium triphenylphosphine, okay, oops, right? It looks really ugly, right? But here's the reaction that ends up taking place. Okay, like that. So, right. So like that. So okay. So these are really simple, right? So you have the O8, right? The BOH here, right? So you know, Suzuki coupling, right? So. So palladium triphenylphosphine. Okay, so wherever that boronic acid was is going to connect right where that halide is, right? So and there you go. Okay, next one. Okay, right where this is going to connect right where that one is. Okay, so like that. So you end up with like that. Okay, now it's kind of an ugly compound, right? How you would draw it, but that's what you end up with. Okay. Okay, I think this is the last one. Okay, so you can think of this as so oxidation. So we have this concept of oxidation reduction in organic chemistry. Okay, and there's two different types of ways you can do this. Okay, you can think of it as carbon electronegative atom bonds. Okay, particularly things like carbon oxygen bonds. Or if we increase the number of double and triple bonds. Okay, so by that double and triple bonds, if we increase the number of these types, right? So CO, like CO bonds, or then increase the number of double bonds and triple bonds in the reaction. If we increase that number, right, it's considered oxidation. If we reduce the number of those types of bonds, it's reduction. Okay, so no big deal. Okay, so here we go. So are these oxidations or reductions? Okay, so here we go. So okay, so we're going here, chlorine. Okay, and so we have, right, so what are we looking for, right? So we're looking for the CC, right, C triple bond C, right, and then C electronegative, right, so electronegative. Right, so we have one here, right, so we have one carbon oxygen bond, right, and here we have two carbon electronegative, right, so we have this one here and this one here, right, so we're going from 1 to 2, so it's an oxidation. The number goes up, so it's oxidation. Okay, so we go from KMnO4, right? So, right? So we're going from, right? So we're going from these two here, right? So this one here, and that one, right? So this one here, that's 2, right? C double bond O, right? So, and then here we're going from those 2 plus that one plus 1, right? So 3, right? So we're going from 2 to 3, right? So this is an oxidation. Okay. This last one here, sodium borohydride, right? Right, we're going from 2 to 1, right? So that's a reduction. There we go. That's what we got.